Good morning and welcome to the physical world, or the world of physics. Today what I'd like to talk about to wrap up Unit 9 on periodic motion is the idea of amplitude. And you know from the book that amplitude is defined as the maximum displacement from equilibrium. So in a pendulum, this swings a certain amount, right? It's displacing from equilibrium, restoring forces, slowing it down. That maximum point is the amplitude of the system. But amplitude conceptually also is a measure of the energy of the system. The larger the amplitude, the more energy is in that system. So when a pendulum is just, or a child on a swing is just swinging a little bit, that's low energy, right? But as the amplitude increases, you get more and more energy in the system. And because of that, we can actually think about oscillating systems, or systems in periodic motion. They're basically devices for exchanging energy from one form to the other when we think about amplitude that way. So if you're bouncing on a trampoline, right, at the maximum displacement down here, your velocity is zero, so there's no kinetic energy in the system, but there's a lot of spring potential energy. Then that's released, and when you hit equilibrium, all that spring potential energy is gone, and you have maximum velocity. As soon as that person leaves equilibrium, gravity starts to slow them down. Now at the top here, they've got maximum gravitational potential energy. So up here, they've got MGH. Let's just call this MGH3. Down here at equilibrium, they've got kinetic energy. And down here, they've got spring potential energy. And you know, by the law of conservation of energy, that all three of these are equal. And so that gives us a way to crack these problems in a very simple way. Now, let's move over here to the pendulum. And what a pendulum is trading off is, when you take the pendulum and you pull it back like this. Let's go do that. So we've got our pendulum here. It's in equilibrium, just sitting there, and then we grab it and we apply a force over a distance. In other words, we do work and input energy into the system, raising it up. When we let it go, that's going to exchange that energy to kinetic, potential, kinetic, potential, kinetic, back to potential on the other side. So what we have here, a couple of things you want to notice is, at the maximum amplitude, the bob comes to rest, right? And so the kinetic energy up here is zero. However, we've now displaced this a certain delta H from here. And so we now have a potential energy of mgh, let's just call this H2 up here, and we'll call this 0. And down here, it's come back down to height 0. We'll make this 0. And so the potential energy is 0, but its movement is fast. So it has kinetic energy down here. Then up here has, again, mgh2. And this has to equal that. And that's a way to crack those problems. Now, with a spring mass system, where we have some kind of mass, and we say for simplicity this is frictionless right here, and it's at equilibrium right here, and so we're going to call that position 0. And these amplitudes, we'll call this negative capital A. Amplitude is capital A because acceleration is small a. And this is A in meters. And once we let this go, right, it's in equilibrium here. As we pull it this way, the spring is extended, and so it provides a force in that direction. It's going to start oscillating back and forth. And here, where the spring is at its normal state, there's no spring potential energy, but it's moving. So the energy is 1/2 mv squared. Here, energy will be 1/2 k negative a squared. And here the energy will be 1/2 k a squared. Now you can calculate the velocity anywhere in this system by subtracting the spring potential energy at that point from the total spring potential energy, and whatever's left over is going to be the velocity. Now, there's a couple other points we want to look at here before we move on to taking a look at our graphs. Okay, number one, when we talk about a cycle here, there's something I think a lot of you may have noticed. Right, we defined a cycle, we define a cycle by observing the system at one point and following it until it returns to that point, right? And if we take this as point A, and it swings down here, then back to here, clearly one cycle is that swing, right? But if we take this position here as B, the equilibrium position, and we start there, it appears that a cycle is then cut in half. But what I want you to notice is that mass has returned to point B here, but it's going in the opposite direction. So the system has not returned to its original state. It's got to go back here and then to here. So really the cycle is from A, let's call this point C, to B in that direction, to C, to B in that direction, and then back to A. Now, the point about doing problems, and they're going to try to trick you in Pearson, is if you are given the time for it to swing through the equilibrium point twice, you've gotten half a cycle. And if you're given the time for it to go from maximum amplitude to equilibrium, you've gotten a quarter cycle. Now, let's take a look at how that works graphically. Right, if we have a graph of amplitude, and in the case of a pendulum, amplitude is the angle of the swing versus time. And we start off right here, the amplitude is 0. That's going to swing up to positive A, back through equilibrium, and then back to the starting point. And because it's oscillating, it will continue like that. What you need to be able to identify on a graph then, and this is negative A, right, when it hits here. This is 0. You need to be able to first identify the amplitude, which will always be the maximum displacement from equilibrium. You also need to be able to mark off a single cycle. And from that, numerically, you should be able to identify the period and the frequency. Now, same thing happens here. This spring mass system, and we can, in fact, use the exact same graph. The spring mass system starts at equilibrium, displaced to positive A, then comes back through to negative A, and then back to equilibrium. And so that should be enough to set you up to handle Pearson. Other than that, study pages 456 to 459, and good luck.